Let's look at the lecture notes for section 2.7, inverse functions. We have our list of learning objectives, and we'll hit each one of those here during this session. May have to break it up in a couple of sessions. It's kind of a long section from the book. So we're going to develop the concept of an inverse function and its properties. First, we have to recognize if a function is one-to-one or not. And one-to-one means one x value corresponds to one and only one y value, and vice versa. There can only be one x going to one y and one y going to one x. In order for a function to be one-to-one, it must pass the horizontal line test. And it's just like the vertical line test, but we're going in a horizontal fashion. So to determine if our functions are one-to-one, we will draw a horizontal line, and if a horizontal line intersects that graph at more than one point, it's not a one-to-one function. We may not always be given the graph, but given this equation with the square root, we should recognize the basic shape is that arc shape, and it would pass the horizontal line test. So this one would be one-to-one. The squaring shape, we should know the basic shape of that. It's a parabola. Will it pass the horizontal line test? No, it wouldn't pass the horizontal line test. And then finally, this cubing shape that I've sort of stretched out a little bit, it would pass the horizontal line test because horizontal lines will intersect at only one point. Now that we can figure out and determine if a function is one-to-one, then we can find inverse functions. And so only one-to-one functions will possess inverses. That's important. We can't do any of this work on a function that's not one-to-one. We have to have one x going to one y and one y going to one x in both directions. And what an inverse function is going to do is it's going to go backwards. It's going to kind of undo the original function. So given these three functions, that they're all one-to-one, let's talk about their inverse. And let's just recognize some patterns. Here's a function f of x equal x plus 5. Notice its inverse. I'm calling it g of x, but its inverse is x minus 5. So it's the opposite. What undoes a plus 5? A minus 5. Here's a function, f of x, which is a one-to-one function, which is 7x. What's the opposite of multiplying something by 7? Well, it would be dividing something by 7. They undo each other. They're inverses of each other. Finally, the last two. We have to be careful. I've told you that x squared right here is a one-to-one function because I'm saying it has an inverse. But we just saw above that an x squared can't have an inverse because it's not one-to-one. It doesn't pass the horizontal line test. What we're going to do on these functions that aren't one-to-one is we will force them to be one-to-one by making some type of statement or some type of restriction after the function. What this restriction does is it makes us consider only half of the parabola. And if I'm looking at half of a parabola is a one-to-one function. So that statement says, okay, we're all right. That one's a one-to-one function, so we can perform our operations. So if I have an x squared, what's the opposite of squaring something? Well, square rooting. So square functions and square root functions will run as inverses of each other because they undo each other. So just out of curiosity, if I had a function x cubed, what do you think its inverse would be? What would be the opposite of cubing something? Well, the inverse would have to be what? A cube root. Those two guys would undo each other. They run as inverses to each other. Let's look at some more properties of inverses. First thing is dealing with compositions, and I have an x missing here, so let me put it in. Working with some compositions. Let's go ahead and do the composition f circle g and g circle f for these two functions. And I'm stating basically that these are inverse functions. They're the two that I was given to you earlier. F circle g means f parenthesis g parenthesis x, which means we're putting the g function inside the f function. When I do that, when I put the g function inside the f function, it looks like x minus 5 plus 5. And what happens here is that the 5's cancel and I'm left with x. Let's go the other way around. Let's do G circle F, which means G parenthesis F parenthesis X, which means we're plugging the F function inside the G. So we're going to pick up the F function and put it inside the G function everywhere there's an X. It's going to look like X plus 5 minus 5. And the two 5's cancel, so we're left with just X. This is going to always happen when we do compositions of a function and its inverse. We're going to see stuff canceling and we'll get an X. Let's see if it happens on this one. F circle G is F parenthesis G parenthesis X, which means the G is going to go inside the F. So we'll pick up the G function and put it inside the F. So instead of 7x, it's going to be 7 times x over 7. Anything cancels? Yeah, two 7's cancel. I'm left with x. I'm just noticing a pattern here. The compositions of a function and its inverse will always be x. Let's do G circle F. G parenthesis F parenthesis X, which means I'm putting the F function inside the G function. So let's pick up the F function, see what that's going to look like, and throw it inside the G function. Oops, I erased the wrong thing. There we go. So picking up the F, which looks like this, placing it inside the G function everywhere we have an X, we end up with 7x over 7, more canceling, 7's cancel, and so we're left with an X. So the pattern we see here is that when we do compositions, the composition of a function and its inverse will always equal x. Let's check out our next part. Let's investigate some more with some ordered pairs. Again, my x's kind of got off of here, so let me write those in. I want you to complete some ordered pairs. I'm going to pick the x values of 0, 1, 2, 3. I want you to complete the y's. Then I'll pick some x values over here of 5, 6, 7, 8, and I want you to complete that list of y values. So go to the f function, plug in the 0, 1, 2, 3, and get the corresponding values. Go to the g, plug in 5, 6, 7, 8, and get the corresponding y values. Here's what we'll notice. Notice that the x values over here are the same as the y values over here. And the y values over here are the same as the x values over there. So when we have a function and its inverse, we see a swapping of ordered pairs. And x comma y becomes a y comma x. So a comma b becomes b comma a. How about domains and ranges? Remember, domain is your set of x's, range is your set of y's. Notice the domain of the function f gets placed over here in the range position for the inverse function. And the range on the original function becomes the domain for the inverse function. So the note here is that the domain and range are swapped. And one last investigation, and that has to do with a function and its inverse graphically. So let's graph these two on the same coordinate system. So let me take this one, graph it in blue, noticing that it's a parabola shifted up 2, but the x greater than or equal 0 says I'm only going to consider half. So let's graph half of a parabola up 2 units. That's the point 0, 2. Now let's graph g of x, which is the arc shape that's been shifted in what direction? -2 will tell me I'm going right 2. That one goes right 2. So that ordered pair would be 2, 0. Notice how the ordered pairs are swapping from the function to its inverse. 0, 2 becomes 2, 0. And let's just graph the arc shape that's been shifted right 2, and it's going to look like that. So notice the graphs of f and f inverse. They're very similar in shape, and actually they are going to be symmetric to each other about this bisecting line. If I folded my page along this line, both the blue and the pink shape should overlap each other. This is the line of symmetry. The line of symmetry is this bisecting line, and it's the line y equal x. So the symmetry, they're symmetric with respect to the line y equal x. That's a pattern for symmetry. So we've looked and investigated all the different patterns and characteristics and properties of a function and its inverse. Now let's just state those using the inverse notation. So I haven't pulled this out yet, but this symbol right there is our symbol for an inverse function, f minus 1 of x. So whenever we have an inverse, we'll usually call it by this name instead of the f and the g that we used earlier. So the properties of a function and its inverse are these. We saw this earlier. If you have an ordered pair on the function AB, then on the inverse it becomes BA. We saw that happening. We saw this happen. The domain of f becomes the range of the inverse, and vice versa. The range of f becomes the domain of the inverse. They're swapped. Domain, range get swapped from a function to its inverse. We also saw these compositions. When we composed f and g circle f, we ended up with an x. Well, I'm just stating it here using the actual name, which is f minus 1 of x. Compositions will always equal x. An important note here is we will use this property when we're asked to verify that two functions are inverses. There'll be some problems that you have to verify. This is what we'll do. We'll just show that f circle g and g circle f are equal to x. And then finally, the symmetry. The graph of a function is inverse or symmetric about the line y equal x.